Hello everybody! Here we are starting chapter 7 and we're going to be learning about all things exponential and logarithmic in this chapter. So if you've been curious about logarithms, this is your lucky day. Maybe not today, but your lucky chapter. And hopefully I remembered to go over this exercise with you in the Zoom meeting, but just in case I didn't, and also just to recap real quick, I'm going to do a real fast summary of this graphing that we were doing. And I want to also mention that if you were graphing by hand, something like y equals 2 to the x, just like anything that you graph by hand, you could find a few points. Let's say x was -2, -1, 0, 1, and 2. 2 to the negative second is 1/4. 2 to the negative first is 1/2. 2 to the 0 is 1. 2 to the first is 2. 2 to the second is 4. And when you plot those points, you're going to get something that looks like this. So that's our exponential growth shape. And so when we looked at these with the calculator, we started by looking at y equals 2 to the x, y equals 3 to the x, and y equals 5/4 to the x. And you can see that mine were color-coded, so I have blue, red, and black corresponding to the graphs below. So these all have exponential growth shape. So they all have a shape like so. The steepness differs depending on the base. The base of 2 is not as steep as the base of 3. And the base of 5/4 is not as steep as the base of 2. The smallest the base can be, well, I should say the base cannot be 1, so it has to be greater than 1. Actually, that's not true. The base cannot be 1, and the base has to be greater than 0. And over here we see some bases that are less than 1. Sorry for telling you a lie there for a second. Whew, that was close. Okay, so we see that these are all exponential growth when the base is greater than 1, and the steepness changes depending on the base. And then the 3 over here, 1/2 to the x, 1/3 to the x, and 4/5 to the x, those all represent exponential decay, and the steepness depends again on the base. So 1/2 is not as steep as 1/3, and 4/5 is not as steep as 1/2. So the closer the number is to 1, the less steep it is, and the closer the number is to 0, the more steep it is. Another thing we get from the calculator activity is the relationship between y equals 2 to the x and y equals 1/2 to the x. So if you look at these graphs here, you see that they are reflections across the x-axis. And I want to justify that for you algebraically. So let's say we start with y equals 1/2 to the x power. Wouldn't you agree that 1/2 is the same as 2 to the negative first power? And wouldn't you agree that if we use our exponent properties, this is the same thing as y equals 2 to the negative x, or opposite of x? So what we're seeing if we think about transformations is that 2 to the x has changed to 2 to the opposite of x. And it turns out when you take the opposite of x in your equation, you have a reflection across the y-axis. And we see that exact same thing in y equals 3 to the x and y equals 1/3 to the x. They're reflections across the y-axis, as well as the one with the 4/5 and the one with the 5/4. It was 5/4 to the x, 4/5 to the x. Okay. So let's start today's notes, and I confess that I did not check to see what notes number we're on, and I am at home, so I don't have that information. You can figure that out, notes number ? Let's talk about the general form of exponential functions. According to our book, these are the letters that they use, and I just like to be consistent with the book. Y equals a times b to the x. A is not part of the base. B is the base. A is just a number we're multiplying by after raising b to a power, so a is really the vertical stretch or shrink factor. A cannot equal 0. Otherwise, all you have is y equals 0, and that does not have an exponential shape. The base b has to be greater than 0, and the base b cannot be equal to 1. If you had y equals 1 to the x, it would just be a flat line. And a more simple equation is y equals b to the x. And so we're going to call that our parent function. And I like to say that b is the base, but in your book it also calls b the growth factor. I suppose if it wasn't growth, it would be the decay factor. So it's the growth or decay factor. All right. So in this lesson today, we're going to start by talking about the main characteristics of exponential functions, their graphs, and then we're also going to look at transforming them using all the transformation information we already know, and then we're going to end with some applications. So those of you who like to see the real-world applications, today is your lucky day. So let's start with y equals b to the x, where b is greater than 1. So that would be exponential growth. So we have this kind of shape right here, just kind of keeping it general without actually having a scale. The y-intercept always has to be the point 0, 1. If you take your base b, raise it to the 0 power, you're going to get 1. So we could mark that on the graph as well. What's the domain? Well, x can be any real number. You can take a positive real base and you can raise it to any real number you want. Doesn't have to be an integer. It doesn't even have to be rational, and you will get an outcome, a real outcome. So the domain is all real numbers. Of course, if we want to, we can write that as negative infinity to infinity. Now for the range, if you take a positive base and you raise it to a power, you're always going to get a positive outcome. You're not going to get 0, you're not going to get a negative. Even if you raise your positive number to a negative power, you don't get a negative. So the range, the set of numbers from 0 to infinity. And you can always write that as y is greater than 0. Notice that this graph is increasing, meaning as we move from left to right, the y values are going up. And we have this new term, this might be new to you, it's called asymptote. An asymptote is a line that the graph gets infinitely close to. Now there is a possibility that you have heard the word asymptote before, and you may have even heard it defined as a line that the graph doesn't cross. That's not an accurate definition. It's true for this particular graph, but there are lots of different kinds of graphs that have asymptotes, and some graphs cross their asymptotes. In fact, here's a quick example of a function that gets infinitely close to a line the further out you go. It gets infinitely close to the line y equals 0. So that's the asymptote, but it crosses it infinitely many times. So for your definition of asymptote, I would just like you to think of it as a line that the graph gets infinitely close to. So what line is this graph getting infinitely close to? It looks to me that as x heads toward negative infinity, y, or f of x, if you want to call it that, is heading toward 0. Remember when we used that notation in chapter 5? I'm going to draw this as a dotted line, and that line is our asymptote, and it has equation y equals 0. Okay, that's exponential growth. Let's do the same thing for exponential decay. And in this case, our function is y equals b to the x, same thing, but we're looking at bases between 0 and 1, like in the beginning when we looked at the base 1/2 or 1/3 or 5/4. So the shape of the graphs is something like this, but the y-intercept is still the point 0, 1, because you take your base, you raise it to the 0 power, you still get 1. The domain is still all real numbers, and the range is still y is greater than 0. This graph is decreasing, going down as you move from left to right, and the asymptote is this dotted line here, still the line y equals 0. Okay. Now that we know the basic function, we can use transformations like we've done in the past to graph more complicated versions. And I'm going to do this one step at a time. I'd like you to be comfortable with graphing by hand as well as graphing by calculator, so sometimes we do a little bit of each. And what I'm going to do is start with the parent function, which is y equals 2 to the x. It says include at least 3 exact points. So how about if I use, let's see, -1, 1/2, 0, 1, and 1, 2. And for a scale, I'll just go by ones, even though it's going to be kind of squished together there a little bit. So we have that, but if we did 2, 4, and we also did 3, 8, it's going to grow pretty rapidly. Okay, there's our parent function, and here is our asymptote. I like to draw the asymptote in there as kind of a boundary line. Okay, the first transformation we're going to do is multiply it by 3, and that's a vertical stretch. So that's going to make every point 3 times as tall as it previously was. So the point that had a y-coordinate of 1/2 now has a y-coordinate of 3/2. The point that had a y-coordinate of 1 now has a y-coordinate of 3, and the point that had a y-coordinate of 2 now has a y-coordinate of 6. The graph is still going to get infinitely close to the line y equals 0, so that's still the asymptote. Now finally, we're going to subtract 1. So do you remember what happens to a graph if you add or subtract a number outside the function, like outside the exponent? That would be shifting it up or down. So in this case, we're shifting the whole graph down 1. So that's the transformation. So we can take the previous y-coordinates and we can subtract 1 from them. And it's a really good idea to take your asymptote and shift it down 1 and do that first. So let's plot the points. -1, 1/2, 0, 2, 1, 5. And make sure that you make your graph come close to the asymptote. If you don't draw the asymptote, you might just make your graph come close to the y-axis again, or excuse me, the x-axis again, but it's supposed to be coming close to the asymptote. Okay. So here's one more. And this one has a base of 1/2, so it's going to be exponential decay. Let's start with the parent function, y equals 1/2 to the x. And I'm going to just find some points real quick. -1, 0, 1. We have 2, 0, 1/2. And we can plot those points. We could do -2, 4 and -3, 8 if we want to, just to get a little better idea of the shape. And then let's put that asymptote in place. Okay? Now we have a couple of other transformations. So we have a shift to the left, and we also have a reflection across the x-axis. If you think about that, one of those is a horizontal move, one of those is a vertical move, so it's not going to matter which order we do those in. So suppose I start with the negative, and I just reflect my graph across the x-axis. So that means that's going to take the opposite of all the y-coordinates, and reflecting it across the x-axis is not going to change the asymptote. Let's go ahead and put that in place. And then we can plot these points. Okay. Finally, we're going to shift the graph to the left too. And shifting it to the left or right is not going to change the asymptote. So let's keep that in place. And then what we're going to do is subtract 2 from all of our x-coordinates that we previously had. Leave the y-coordinates the same. And then we can plot those points, -3, -2, -2, 0, Hey you guys, it took me long enough, but I finally realized my mistake. That should be a 1. That should be a 1. And that should be a 1. Okay, -2. So that means that should be a -1, and that should be a -1. Okay, I graphed it right. I don't know why I didn't catch it. So -2, -1, and then -1, -1/2. There we go. Sorry about that. Okay, so let's wrap it up with exponential growth and decay models. All right, so you're going to be doing different kinds of story problems in this chapter. We're starting with this particular type where you're given the percent that something grows or decays. And so if it grows, you're going to use this first equation, and if it decays, you're going to use the second equation, but you can see that they're basically the same thing. So y in both cases is the final amount, or the amount at time t. We don't need to define it twice. A is the initial amount, which means the amount at time 0. R is either the percent of growth or the percent of decrease. So in this case, it's the percent of growth, and in this case, it's the percent of decrease. And we need to convert it to a decimal. So then 1 plus r would be known as the growth factor. That's going to be our base. And 1 minus r would be known as the decay factor. That's going to be our base. Generally, t is time. And it's not always years. Sometimes it's years. I think in the problems that we're about to do, it's years, but it doesn't have to be. It could be other units of time, like days or hours or minutes or something. All right. So here's our example of growth. In 1995, the population of your town was 300,000. From 1995 to 2015, the town population grew at an average rate of about 2.4%. Part A, write an exponential growth model for the population of your town t years after 1995. When a problem says write a model, they mean write the general equation. So this is growth, so we're going to use y equals a times 1 plus r to the t. And we know the initial population was 300,000, so that's the value for a. And we know the rate of growth was 2.4%. We convert that to a decimal and we get 0.024. And then for our final answer, we can just go ahead and add 1 and 0.024. So we have y equals 300,000 times 1.024 to the t power. So now we're going to use that model for part B. About how many people lived in your town in 2010. So in 1995, we're calling that t equals 0. So in 2010, we're calling that t equals 15. So we substitute 15 into our equation for t. We put that into the calculator, and we get approximately 428,174 people. And then finally it says, use your calculator to graph the model. Okay, so we type the equation into the calculator, and then we have to set a good window. We've done this before where we've used our calculator to model things. We know we have to know about the model in order to determine a good window in order to see the graph. So for the window, the x values are the time. So I went up to 22 because that would be the year 2017, and it says this model goes till 2015. And I went to -1 because I'd like to see the y-axis. And if I don't use any negative x values, I won't see the y-axis. And then for my y minimum, same reasoning. I went to a negative value because I like to see the x-axis, and I went all the way up to 500,000. So I changed my scale to have a tick mark every 50,000 units on that axis. So this is what the graph looks like. Okay, we're only seeing a little piece of it, so we're not seeing a huge amount of exponential growth, but still it's an exponential function. All right, last one. This is an example of decay. A new car costs $25,000. The value of the car decreases by 15% each year for the first 5 years. Do you know the word for that? That's called depreciation. So appreciation, in addition to saying something nice about someone is when a value goes up, and depreciation is when a value goes down. So let's write the model. So we need to use our decay model, which is y equals a times 1 minus r to the t. And the initial value was 25,000, so that's our a. And the amount of decrease, 15%, converted to a decimal is 0.15. So then we'll simplify that, and we get the model y equals 25,000 times 0.85 to the power t. What is the car's approximate value after 3 years? All we have to do is take our model and substitute 3 in for t. Oops, let me put the 3 in there. And I'm going to round to the nearest penny since it's money. We get $15,353.13. And then to graph the model on the calculator, just follow the same steps we did on the last problem. I'm just not going to do it right now because I know you guys like me to keep these videos short, and I'm already at 20 minutes plus. So type it into your calculator, think about a good window for these numbers, and then make sure you can see your graph well in your window. Okay, so your homework, you do have a couple of story problems at the end, I think 41 and 35, so go ahead and use your graphing calculator for those graphs. And for the other graphs that are more simple, I'd like you to practice doing those by hand. Thanks, everybody.